Hi, welcome to the new lecture. In this lecture, we'll discuss a topic of oceanography, which is continental margins, continental shelves, continental slopes, submarine canyons, and continental rises, which is a very interesting topic of the ocean floor and the ocean bathymetry, we can say that. So, continental margins, as the name suggests, the margin of the continents, because the land areas on our planet Earth, they are very less as compared to the ocean area. So the portion of the continent that touches with the ocean, or the margin of the continent that touches with the ocean, is called the continental margin. So what features they exist on the continental margin? So we can say the ocean floor, it can be divided into three major provinces. Number one is continental margin, which are shallow water areas closer to the continent. As you can see in this picture, this red line, let me highlight it. So, sorry, yeah, as if you want, you can see the red dot. So the continental margin area, this is the cross section of A and B, which is a cross section of mid-Atlantic ridge that encompasses between the Atlantic Ocean, between Africa, Europe, and North America. So this is A to B, it's a red line, it's a cross section, which is on the transverse section A and B presented here in the top of the image. So you can see the profile here in the blue color. In the continental margin, it is the shallow area which is very much closer to the continent, sorry. Excuse me. So this portion here, which is closer to the continent, it's the continental margin. So the continental margin, these are shallow water areas which are close to the continents. And number two, we have deep ocean basin, as the name suggests. This portion, which constitutes the deepest part of the ocean, which are the deep water areas farther from the land. So this one. And number three is the mid-oceanic ridge. In this case, there is a mid-Atlantic ridge, which is composed of shallow areas near the middle of the ocean. So how are these provinces? These are basically an integral part to the formation. These are plate tectonics processes. They are integral to the formation of these provinces. Actually, these provinces, they are formed by the plate tectonic processes, right? At mid-Atlantic ridge, we have new magma addition up, which further pushes the margins away. So though the process of seafloor spreading, the mid-oceanic ridge and deep ocean bases are created, elsewhere as a continent is split apart, new continent margins are formed. So this figure is major regions of the North Atlantic Ocean, which is a map view and a profile view, bottom and top, showing that the ocean floor can be divided into three provinces: continental margins, deep ocean basins, and mid-oceanic ridge. Now, moving to the next. Uh, Now, we have two types of continental margins. One is passive margin and another is active margin. So, in this figure, you can see we have a rift valley in the middle of the figure, and on the left we have passive continental margin, and on the right we have active continental margin. Now if you'll see closely what's the difference between the passive and active. So the active continental margin is the place where all the action is happening. Here you can see there is a subduction going on. One plate is being overridden by another plate, because the ocean plate is denser, so it goes down, and the continental plate is much lighter and it overrides the continental plate, so the oceanic plate. So this area where the subduction is going on, it is called as active continental margin. And you can see there is continental shelf portion, continental slope portion, and there is oceanic trench portion as well. Now moving to the left side where we have passive continental margin, there is no subduction going on, so there is a direct continental shelf and then slope, rise, and then you have directly abyssal plain. So there is no trench in between. So this is the basic difference between passive and an active continental margin. Now moving to the next slide. So let's discuss about the continental shelf. So before going into the text, So the continental shelf is the flat zone basically. You can see in the figure the features of a passive continental margin. This is a passive continental margin because there is no trench here. So we have continental crust, so which is, then follows and changes into the ocean crust, and then there is water on the top. So continental shelf portion is the flat uh, portion of the continental margin. This whole consists of continental margin, which has continental slope and rise as well. We'll discuss in next slides, but this slide talks about the continental shelf, which is a gently flat zone area extending from the shore beneath the ocean surface to a point at which a marked increase in slope angle occurs, called the shelf break. So gradually up to the portion, onto the shelf break here, because here the angle increases after that. So it is usually flat and relative featureless area because of marine sediment deposits that can contain coastal islands, reef and raised banks. So the underlying rock is granitic in nature, which is granitic continental crust. So the continental shelf is geologically part of the continent, and accurate seafloor mapping is required or is essential for determining the extent of the continental shelf, because how long is it, the continental shelf extends from the continent into the ocean. So continental shelves, they also vary depending on the local geology and topography. For example, the average width of the continental shelf is about 70 kilometers, but it varies from a few tens of meters to 1500 kilometers even. So the broadest shelves occur off the northern coasts of Siberia and North America in the Arctic Ocean. And worldwide, the average depth at which the shelf break occurs is around 135 meters. And however, in Antarctica, the shelf break occurs at 350 meters. So the average slope of the continental shelf is only about a tenth of a degree, which is similar to the slope given to a large parking lot for drainage purposes. So it's a very, generally speaking, very low slope, about tenth of a degree. So this is again an example of a borderland in the California, which California shares with the Pacific Ocean. So what has happened that sea level has, fluctuated over the history of Earth, causing the shoreline to recede and then uh, transgress, migrate back and forth across the continental shelf. So which actually, influences the position of the continental shelf. So when colder climates, they prevailed during most of the recent ice age. So more of the Earth's water was frozen as glaciers on the land. So sea level was much lower than it is today. And during that time, more of the continental shelf it was exposed. So again, number two, the type of continental margin determines the shapes and features associated with the continental shelf. So what type of margin is there? So it will also determine the shapes and features. For example, the east coast of South America, as you can see here in the figure, it's the eastern coast of the California. The east coast of South America has a broader continental shelf than its west coast. You can see the continental shelf goes up to here, and here after that continental slope occurs. So you can see it's a broad area which consists of a lot of small islands. In contrast, the convergent active margin present along the west coast of South America is characterized by narrow continental shelf and the shelf broke for the shore. For transform active margins such as along California, the presence of offshore faults produce a continental shelf that is not flat. Rather, it is marked by a high degree of reliefs, which includes islands, shallow banks, and deep basins called a continental borderland. So continental shelf, the features of continental shelf, it again depends on the type of continent margin. So if we have active margin, we have passive margin, and then we have transform active margin. So this picture here is a transform active margin of the California. You can see the transform San Andreas fault going in there. So this transform active margin, it consists of a broader shelf area, and again not only shelf, we have lots of islands also present in this. So now let's discuss about the continental slope. So we know that the continental slope is the portion which lies beyond the shelf break and where the deep ocean basins begin. So total relief in this region is similar to that found in mountain ranges on the continents. The break at the top of the slope may be from 1 to 5 kilometers above the deep ocean basin at its base, and along convergent active margins where the slope descends into submarine trenches, even greater vertical relief is measured. Off the west coast of South America, for instance, the total relief from top of the Andes mountain to the bottom of Peru-Chile trench is about 15 kilometers. So, talking about worldwide, the slope of the continental slopes averages about 4 degrees but varies from 1 to 25 degrees. A study that compared different continental slopes in the United States revealed that the average slope is just over 2 degrees, and around the margin of the Pacific Ocean, the continental slopes average more than 5 degrees because of the presence of convergent active margins that drop directly into deep offshore trenches. The Atlantic and Indian Oceans, on the other hand, contain many passive margins which lack plate boundaries, thus the amount of relief is lower and the slopes in these oceans average about 3 degrees. So now let's discuss about submarine canyons and turbidity currents. As the name suggests, submarine canyons is the canyons which are present underwater. So here it's a block diagram of turbidity currents and how the turbidity currents move down the slope and the submarine canyons, right? So this is a continental shelf area, right? And then the slope starts and then we have deep ocean basin. So in the shelf we have submarine canyons when there is some landslide underwater going on, and the sediments, it moves downward under the influence of gravity. And how does it move? It moves in the form of turbidity because of the turbidity currents. So you can see the inset, the turbidity currents, where there is a graded bed sequences, and how there are 3 turbidity current flows. We can see the large grain size which is at the bottom, and as we move top, the finer grain sediments. They are present. So we have 3 cycles of turbidity, and in individual current deposit we have a graded bedding sequence from coarser to finer as we move from bottom to top. So turbidity currents move downslope, eroding the continental margin to enlarge submarine canyons, and then deep sea fans are composed of turbidite deposits, which consists of sequences of graded bedding. So these are the deep sea fans, so which has the sequence particularly of the graded bedding. Okay. Okay. The continental slope and to a lesser extent the continental shelf exhibit submarine canyons, as it is evident from the figure here, which are narrow but deep submarine valleys that are V-shaped in profile view and have branches or tributaries with respect to the overhanging walls. These resemble canyons formed on land and are carved by rivers and can be quite large. And in fact, the Monterey Canyon of California is comparable to the size of Arizona's Grand Canyon. So they can be so large. So how are these formed, which I have discussed already? How are the submarine canyons formed? So initially it was thought that submarine canyons were ancient river valleys created by erosive powers of rivers when sea level was lower and the continental shelf was exposed. Although some canyons are directly offshore from where river enters the sea, the majority of them are not. Many, in fact, are confined exclusively to the continental slope. And in addition, submarine canyons continue to the base of the continental slope, which averages about 3,500 meters below the sea level. And there is no evidence, however, that sea level has been ever lowered that much. So this is a real-time picture of a submarine canyon where a diver is descending into a submarine canyon in Red Sea near Dahab, Egypt. And this is an outcrop picture of a turbidite deposits. How does it look like in an outcrop, which have been tilted and uplifted on the land in California? So each light-colored layer is sandstone that marks the coarser bottom of a graded bedded sequence. So sonar surveys, which is sound navigation and ranging, their side scan surveys along the Atlantic coast indicate that the continental slope is dominated by submarine canyons from Hudson Canyon near New York City to the Baltimore Canyon in Maryland. And canyons confined to the continental slope are straighter and have steeper canyon floor gradients than those that are cut into the continental shelf. So these characteristics suggest the canyons are created on the continental slope by submarine processes and enlarge the continental shelf into the time, through time. Okay, so let's discuss more about the canyons. I mean, this is the figure which compares the underwater canyon, Monterey Canyon, in the Monterey Bay of the west coast of America, to the Arizona Canyon, Grand Canyon at the Arizona Park here, which is around the, this red, green boundary, which is on the Colorado River. It marks the extent of the canyon. So we have Grand Canyon National Park and the Grand Canyons here. So the observations, both direct and indirect, of the erosive power of turbidity current. Turbid word comes from turbidus, which means disordered. So they have suggested these observations that the turbidity currents are responsible for carving submarine canyons. So turbidity currents are basically underwater avalanches of muddy water mixed with rocks and other debris. The sediment portion of turbidity currents come from the seafloor materials that move across the continental shelf into the head of a submarine canyon and accumulate there, setting the stage for initiation of a turbidity current. So trigger mechanisms for turbidity currents include shaking by an earthquake, oversteepening of a sediment that accumulates on the shelf, hurricanes passing over an area, and the rapid input of sediment from floodwaters. Once a turbidity current is set in motion, the dense mixture of water and debris moves rapidly downslope under the force of gravity and carves the canyon as it goes, resembling a flash flood on a land. So turbidity currents are strong enough to transport huge rocks down submarine canyons and cause a considerable amount of erosion over time. So these turbidity currents, they are triggered by earthquake, oversteepening, or a hurricane even under the influence of gravity, and they are responsible for carving these underground submarine canyons. Okay, so now let's discuss about the another feature, which is continental rise of the ocean floor. So the continental rise is a transition zone between the continental slope and the deep ocean floor, comprised of a huge submerged pile of debris. So where did all this debris come from, and how did it get there? So the existence of turbidity currents suggests that the material transported by these currents is responsible for the creation of continental rises. When a turbidity current moves through and erodes a submarine canyon, it exits through the mouth of the canyon. And the slope angle decreases and the turbidity current slows, causing suspended material to settle out in a distinctive type of layering called graded bedding that grades in sizes upward. As the energy of the turbidity current dissipates, large pieces settle first, then progressively smaller pieces settle, and eventually even very fine pieces settle out, which may occur weeks or months later. An individual turbidity current deposits one graded bedding sequence. The next turbidity current may partially erode the previous deposit and then deposit another graded bedding sequence on top of previous one. So after some time, a thick sequence of graded bedding deposits can develop on top of the other. These stacks of graded bedding, which make up the continental rise, are called turbidite deposits. Let me show you the picture again. Okay, moving forward. So this is a picture of a continental rise. I mean, this is an example of an Indian Ocean. So we have Indus River bringing huge amounts of sediments which are deposited in this fan, right? So this is a passive margin fan, and B, this is a sonar view of Chatham fan, which you can see. I mean, this is a leaf, this is a channel, and this is a fan. How the fan, it has a slope, it grades downwards. So it is which rises 400 meters, that is 1,500 feet above the surrounding floor, which is a sea floor, and this fan is rising, you can see here. So as viewed from above, the deposits at the mouths of submarine canyons, they are lobate or apron shaped, as you can see from the Indus, and consequently these deposits are called deep sea fans or submarine fans. So deep sea fans create a continental rise when they merge together along the base of continental slope. Along convergent active margins, however, the steep continental slope leads directly into a deep ocean trench, and sediment from turbidity currents accumulate in the trench, and there is no continent rise. One of the largest deep sea fans in the world is the Indus fan, a passive margin fan that extends 1,800 kilometers south of Pakistan. And the Indus River creates large amount of sediment from the Himalayan mountains to the coast. And this sediment eventually makes its way to the downward, uh, makes its way down to the submarine canyon and builds the fan, which in some areas has sediment that is more than 10 kilometers thick. So the Indus fan has a major submarine canyon channel that extends seaward onto the fan, but soon divides into several branching distributary channels. These distributary channels are similar to those found on deltas, which form at the mouth of streams. On the lower fan, the surface has a very low slope and the flow is no longer confined to channels, so it spreads out and forms layers of the fine sediment across the fan surface. The Indus fan has so much sediment, in fact, that it partially buries an active mid-ocean ridge, the Carlsberg Ridge. So this is the map of the Indus fan, and on the bottom picture, it's the sonar perspective of Southeast Asia's Chitham fan, which rises 400 meters above the surrounding sea. So this is it for the current lecture. If you have any questions, you can write in the comment box. Thank you. Bye-bye.